The fifth step of any typical instability analysis is to assume a normal mode for the disturbance. We don't have enough information for an arbitrary disturbance appearing on the interface, but I only want to understand the condition under which the disturbance grows or decays. So, in the different instability analysis, it's customary to suppose the disturbances eta and phi hat here in our case. These are the Schulze and Schlichting traveling waves, and you see the amplitude of disturbance of eta is eta 0, and the amplitude of disturbances of a potential function for fluids 1 and 2 is phi prime 1 and 2, and e to the power of I is the root of -1. Alpha is the wave number of the traveling wave, minus sigma is the frequency of the traveling wave. Again, these are normal modes or the Toomey and Schlichting TS traveling waves or normal modes because they are harmonic, e to the power of complex number, and normal because they are independent of each other. As you see here, if alpha is a real number, x is again a real number, so the product of I and alpha x is a real number. As you know from your knowledge of basic mathematics, e to the power of a complex number is a harmonic function, which is a bounded function. So when alpha is a real number, speaking about the growth of a disturbance with x is meaningless. So if you want to investigate the spatial instability, alpha should be a complex number. Similarly, if sigma is a real number, again t is a real number time, so the product of I and a real number is an imaginary number. E to the power of an imaginary number cannot be an unbounded solution. So when you are going to investigate the temporal instability, so sigma should be a complex number. If you are going to investigate spatial instability, alpha should be a complex number. Here in our analysis, alpha is a real number, so we want to investigate the growth or decay of a disturbance with time, or our analysis is a temporal instability analysis. So alpha is a real number, but sigma can be a complex number. Okay, so sigma is a complex number. If sigma is a complex number, it has two parts, an imaginary part and a real part. Again, a real part of the sigma has nothing to do with the instability, because if the real part is multiplied by I and e to the power of a complex number is a bounded function. So the imaginary part of sigma is important or plays the key role in instability analysis because of the minus sign here. If the imaginary part of sigma is a positive number, the disturbance will grow because the power of the exponential function is a positive number. And if because we have a minus sign here, and the product of two i's is -1. So if the imaginary part of sigma is a positive number, this e will the power of e is a positive number, and the disturbance will grow to the infinity. So in our temporal instability analysis, the imaginary part of sigma is important, and alpha is a real number.